let's talk about the theorem. This is the work energy. Say this is a floor. And this is the initial position. Initial position. We can assume this is initial velocity V naught. Okay, the box is at initial velocity V naught. When we apply external force or push, say for example, push, this is the external force to the system. We call it FA. That's the symbol APP. External force. Because of this external force, it will move and it will reach here. So this is the final position of the package. This is the final position. You can say at that point, the initial velocity changed to V. So this is a final velocity. Okay. The total distance covered here is, say, that distance is D. Okay. This is the situation. Let's draw a force diagram, force diagram for the package. If the package is represented by dot, our external force applied is FAPP, applied force. Friction will be towards left, right? This is the force due to earth, Fe, and Fn is the force exerted by surface along y-axis. So for simplicity, I will consider this is my x-axis. I will consider this as y-axis. Okay. So now, if I consider my coordinate system up positive, down negative, left negative, and right positive, I could write net force F net along x-axis. So we have two forces along x-axis, which is F applied is plus and friction will be minus based on this picture. Now, similarly, we can say along y-axis, so along y-axis, the net y equals, you can see here, Fn minus Fe or Fg. I don't know what symbol I use. Okay, Fe. They will cancel because Fn and Fe in this case have equal magnitude, right? So they cancel. So this means in our case, if you combine these, our F net will be, net force will be just F applied minus F. Okay. So based on that, the rule, the work energy theorem, actually relates that the work done by the the work done by the total force, net force, which is work done by the net force equals change in change in change in kinetic energy. Change means final kinetic energy, which will be half mv squared. Initial kinetic energy is half m v initial squared. So work, yeah, total work done by the net force, which is clearly in our case, this equals F net times d cosine 0. Cosine 0 is 1, so you can just write F net times d. So this is the work energy theorem. This basically relates work and energy. We can do a very similar problem over here. Say we have a box. We have a box here. The box is here, mass m, and it is at rest. When it covers a distance of 4 meters, starting from this, because of the applied force, we are pushing parallel to the surface. So this is the external force. The object will be at 4 meters. At that point, say its final velocity is v. We want to know that. We don't know that now. We need to figure out. So clearly, this is your initial position. And that is final position. So as before, if you draw the force diagram for this mass, we have forces Fn, Fe, Fe, F applied, and friction, right? In our case, they give mass equals 2 kilogram. V initial is equal to 0 because at rest. V final, we don't know. Applied force is 10 Newton. Then we want to use the work energy theorem, which is total work done, W net, is equals to half mv squared minus half initial squared. In this case, as before, what will happen? Fn and Fe will cancel each other. Cancel each other. This is nearly 0 in our case because this is frictionless surface. So we are assuming friction is 0. So the only one force left is F applied times a distance covered, which is d, that they give the distance traveled is 4 meters, right? It's d cosine 0 because they are parallel. F and d are F applied and distance covered are parallel. So half mv squared, because v is equal to 0, that makes everything 0. So we can write F applied is 10, distance is 4, cosine 0 is 1, that equals half, mass is 2 times v squared, that gives us 2 cancel out. So p squared is 40. Then we can take the square root to both sides. That gives us p, which is roughly 3.62 meter. Okay. Now you can use the similar approach for the problem or the practice problem too.